Okay, so let's have a look at example 19. I'm actually going to do a modified version of example 19. I'm going to combine parts A, B, C into one part, and then we can do part D afterwards. So we're just going to do sketch f of x equals x cubed plus 6x squared minus 15x plus 2. And then we'll do part D about talking about whether function's increasing or decreasing afterwards. So step one, let's write down the function we're going to sketch. If you don't like writing f of x, that's okay. Just rewrite it as y equals x cubed plus 6x squared minus 15x plus 2. Same thing. Following our patterns, so step one, let's work out the y-intercept when x equals 0. So y-int when x equals to 0. So essentially setting 0 wherever x is, so we get 0 cubed plus 6 times 0 squared minus 15 times 0 plus 2, so that gives us the 2. So that gets us the point that we need to sketch 0, 2. Then next step, we need to work out the x-int when y equals to 0. So we have 0 equals x cubed plus 6x squared minus 15x plus 2. That's not really a nice cubic to solve, so we're just going to rely on our graphics calculators for now. So if we use our graphics calculator, if you want to solve this algebraically, we would have to do what we did in Unit 1, which was guess an answer, and then set it to be a root, and then do long division to fully factorize it. But for now, calculator. But for now, let's say we worked out what our x-intercepts are. We get x is negative 0.792, 0.14, and 1.78. So that gives us three x-intercepts at negative 7.920, 0.140, and 1.78 across 0 up. Then in step 3, what we need to do is work out the stationary points. So stationary points occur when your derivative, your gradient, equals to 0, because that's the point where your tangent is flat. So step 3, stationary points when the derivative, in this case will be y dash of x equals to 0. So we need to work out what y dash is. So we go back to our original function. We have x cubed, so we differentiate x cubed, we get 3x squared. If we differentiated 6x squared, we get 6 times 2, which is 12x. Minus 15x becomes minus 15, and then the 2 disappears because it's constant. So let's set that to 0. So 0 equals 3x squared plus 12x minus 15. We can divide both sides by 3. So we get x squared plus 4x minus 5. 15 divided by 3 is 5, yes. And then what we can do is to factorize this quadratic. So two numbers that add to be 4 and multiply to be negative 5. So we have positive 5 and negative 1. So then using null factor law, we have that x plus 5 equals to 0. In other words, x is minus 5. Or we have that x minus 1 equals 0. In other words, x equals to 1. So these are our two x values for our stationary points. If we are to sketch any stationary points, we need to find out the corresponding y values. So let's then work out the corresponding y values for these two x values. So we have that when x is negative 5. What's the y value for that? Well, 3 times, so not 3, put it in the original function, not the derivative, the original function, which means it's a negative 5 cubed plus 6 times negative 5 squared minus 15 times negative 5 plus 2. That gets us 102. So that gets us stationary point at negative 5 across 102 up. And then we can work out the y value when x is at 1. That's the other stationary point. Y is 1 cubed plus 6 times 1 squared. So putting it into the original function. So that gets us -6. So we have the other stationary point at 1 across and -6 down. So we have y int, we have x int. We've just solved for where the stationary points are. Point meaning we have an x and y coordinate. Next, what we need to do is to test the nature of the stationary point. So I'll show you both methods, just in case. So the easier method is to do the double derivative, but sometimes the double derivative doesn't always work out, so we just have to resort to the table method. So next step, so that was step 3, stationary points. Step 4, checking the nature. So nature of stationary points. As I said, I'm going to show you 2 methods. So method 1 is using the second derivative. So using y dash dash, because I called the function y, not f. So let's work out what y dash dash is. So let's go back to what y dash was. So y dash was 3x squared plus 12x minus 15. So to get y dash dash, we need to differentiate this one again. So 3x squared becomes 6x, the 12x becomes 12, and the 15 disappears because it's constant. So y dash dash gives us 6x plus 12. So we've got 2 stationary points. One is when x is -5, and the other one is when x is equal to 1. So what we need to do is to put these 2 points into y dash dash and see whether they come up positive or negative or 0. So let's try when x is -5. Well, y dash dash of -5 is 6 times -5 plus 12, which is -30 plus 12, which gives us -18. Now, -18 is less than 0. Less than 0 meaning it's negative. If you're negative, then you're like a sad face, which means you've got maximum worries. In other words, this stationary point is a maximum. So we can say that it's negative, so it's sad face. So therefore, -5, 102. So that stationary point is a maximum stationary point. And then we've got to check the other point. So when x is equal to 1, what's the double derivative at that point? So you replace x with 1. So 6 times 1 plus 12. 6 plus 12, that's 18. 18 is positive. Positive, which means you're happy. So therefore, the stationary point 1, -6 is a minimum, because happy means minimal worries. Minimum stationary point. So that's method 1. If you want to do it the double derivative way. If you wanted to do the table method, or the first derivative way, we can do the following. So method 2 for checking the nature is what you need to do is you need to set up a table of values. So you need to set up a table of x values, and then you need to set up a table of your first derivative values. So it's your derivative or your gradient. Now, how many points do you, or how many tables do you need to set up? Well, it depends on your stationary points. So right now we've got 2 stationary points. One is when x is -5 and one is at 1. So we kind of visualize a number line. So we've got a point at -5. We've got another point at 1. So again, remember when we need to pick points, we need to pick a little bit to the left and a little bit to the right of each of the stationary points. So if we're going to pick something, let's pick something to the left of -5. So let's say -6. We then need to pick something to the right of 1, let's say 2. We then also need to pick something to the right of 5, and then we also need to pick something to the left of 1. Technically, these 2 values can be the same one because there's no other stationary points in between -5 and 1. So something between -5 and 1, let's say -4, or in fact you could pick 0, that will do as well. So that gives us our table of values. So something to the left of the stationary point, so let's say -6, the stationary point itself, something to the right of that stationary point, -4. Coincidentally, -4 is also to the left of 1, the next stationary point, so we don't have to pick another point to the left of 1. And then we can pick something to the right of point number 1, which we can say 2. I mean, you can pick whatever you want. You could pick 10, as long as it's to the right of the stationary point. So these are our values that we're going to set up our table. Of course, we know that the gradient value at the stationary point is 0. It's meant to be flat, okay? So don't forget, this is your gradient function or your derivative. So it is not your original function. It's y dash. It's the derivative function. So essentially, you need to sub in x is -6 into your derivative function. So hang on, let me go back and look at our derivative function again. So our derivative function, we differentiate down here. So our derivative function was 3x squared plus 12x minus 15. Just going to copy that over so I can see what I'm writing. So essentially what that means is, in this box, it's 3 times -6 squared plus 12 times -6 minus 15. If you worked out what that is, that becomes 21. And then this box here would be 3 times -4 squared plus 12 times -4 minus 15, which gives us -15. And then this one here is 3 times 2 squared plus 12 times 2 minus 15, which gives us 21. So what that tells us is that we can kind of compile a visual understanding of what's happening with our gradients. So right now we've got that when it's at -6, our gradient is going upwards because it's positive 21. Then it's going flat at 0 for -5. And then it's going negative because it's -15, so it's going downwards. Then it's going flat at the next stationary point, and then it's going back up again at positive gradient 21. So we can see that at the stationary point of -5, this would have a sad face feel because maximum feel, because it's positive, then flat, and then going down, forming a sad face. And then at the x point of 1, we have a happy face feel, a minimum feel, because it's downwards, then flat, then upwards again. So we can gather from there that, therefore, -5, 102 is a maximum stationary point, again because of the up, flat, down feeling. Around a little bit left and a little bit right of that -5 stationary point. And then we have that 1, -6 is a minimum stationary point. Again, because if you look at a little bit to the left, it goes down, then flat, that back up again. So it forms like a smiley face, a minimum shape. So that's the second method of testing the nature. It's up to you which method to choose. But again, if your second derivative was equal to 0, that tells us nothing. It only tells us that we have a point of inflection, but we don't know if it's a up, flat, up, or a down, flat, down kind of inflection, in which case we still have to resort to a little bit left, a little bit right, kind of a table method to work out the type of point of inflection that we have. So far we've got our x-int, we've got our y-int. We've determined where the stationary points are, both x and y coordinates, and then we've looked at what type of stationary point, whether it's a happy face, sad face, or an like up, flat up, or a down, flat down. Last thing we look at is, are we given a domain? Because if we are, then we need to look at the endpoints. For this question, we're not given any domain values, so our function, we can graph it forever for the whole domain of reals. So then let's just mark in our axes and graph it. So labeling your axes, x across, y up. Looking across, our x values span from about -8 on the left to about, I think about 2 across on the right. So I'm thinking if I go up in 2s horizontally, that should fit. And then vertically I need to, where's our turning point? We need to go up all the way to 102. So maybe in this span we can go up in 50s. So we have 0, 2, 4, -2, -4, -6. I need to stretch it out. I don't have enough space. -8. And then vertically I was going to say 50, 100, -50. And then going down is negative. We don't need that far down anyway. All right, so let's mark our points in. We've got 0 across, 2 up as our y-intercept. So it's really close because our scale is tiny. So labeling 0 across, 2 up. Just going to label it a little bit bigger. We have our x-intercepts at about -7.9. So that's -7.920 at about 0.140 at about 1.78. So that's about here-ish, 1.780. We've got our 2 stationary points, -5 across, 102 up. -5 across, 102 up. So that's about here-ish, -5, 102 up. And then what was the other one? 1 across, 6 down. So at 1 across, about 6 down, that's another stationary point. 1 across, -6. Now, we've marked our points in, and then we can identify our natures. So we know that around the -5 is going to be a sad face, right? Essentially, it's kind of connecting the dots, but smoothly, because it's a polynomial. It's got to be smooth curves. So we know it's got to be a sad face around here that's going to connect down to this intercept. So it's going to go down forever and then go up like into a sad face. Oh, I think I marked into x-intercept wrong. Oh, that's not 0. That's not 0.14. Let's me mark that again. So 0.14 was about this side. So that's for this point over there. That makes more sense. So we know it's going to be a sad face down from that -5 stationary point, crisscrossing that x-intercept. And then we know that's going to pass through the y-int and then the x-int, and then we know it's got to be a happy face. So it's going to do a turning around at that 1, -6, and then go past back up again into the third intercept. So it's kind of look like a snake-ish graph like what I've shown on the screen. So the next step is to, as best as you can, smooth curve joining through all the points of interest. So let me draw that in. So to the best of your ability, I'm going to start here. So I know it's going to go through all those points and have a minimum point down at 1, -6. And I know it's going to have a maximum sad face at -5. And then smooth symmetrical, joining everything back up. And then let me just gonna fix that up a little. I mean, you should be doing this in one stroke, but since I'm zoomed in, it's a bit difficult to do that. Oh, that's a bit too wide of a curve. So let me just zoom out so I can have a bigger perspective. I'm gonna angle it down so that it crosses that x-intercept and goes down like that. To finish off the graph, we need to label the curve. So y equals x cubed plus 6x squared minus 15x plus 2. Out of good habit, domain and range. So domain is all reals because it's a polynomial. Range, our graph stretches all the way down and all the way up. So it's again all the reals.